Everybody, welcome back to our discussion of Chapter 7. We're now on Section 713, the last section in Chapter 7, which is on intermolecular forces in liquids. So we've been talking a lot about the physical states of substances, if something is a solid, a liquid, or a gas. And the physical state of a substance depends on the balance between the destructive forces, the kinetic energy of the particles of the substance, and the strength of the cohesive forces, the potential energy between the particles. And so there's always kind of this balance going on where if a substance is dominated by cohesive forces, it's going to stick together more and is more likely to be a solid. And if a substance is dominated by disruptive or destructive forces, kinetic energy, it's going to be more likely to be a liquid or a gas. And so depending on the strength of these different types of forces can determine whether something's a solid, a liquid, or a gas. And so to undergo a phase change, let's say you want to go from a solid to a liquid, solids are dominated by cohesive forces, so you've got to add enough energy, enough kinetic energy to the substance to overcome the cohesive forces holding it together to get it to change from a solid to a liquid. And to go from a liquid to a gas, same thing. Liquids have about an equal dependence on destructive and cohesive forces, but there's still enough cohesion that to get a liquid to convert to a gas, you've got to break up those cohesive forces by adding kinetic energy. So you heat it up, the substance absorbs that kinetic energy from increasing the temperature, and then when it gets enough kinetic energy, it's going to undergo that phase change to go from a liquid to a gas. So in this section, we're going to be talking about intermolecular forces, which are a type of cohesive force. And we can predict intermolecular forces based on the chemical structure of a compound and whether it's polar or nonpolar. And so by being able to predict how strong the cohesive forces are based on the structure of the molecule, we can get an idea of about how much energy it's going to take relative to other molecules to get it to undergo a phase change. So just based on the chemical structures of compounds, we could compare two molecules, and based on their structure and the cohesive forces associated with those structures, we could be like, hey, this one has way stronger cohesive forces. It's going to take a lot more energy to get it to go through a phase change. So therefore, it's going to have a higher boiling point, or it's going to have a higher melting point. And so this is what IMFs allow us to do. And this is why they're important, because we can use them to rank and to place molecules on kind of the scale of weakest IMFs are going to take the least amount of energy to undergo a phase change, and the strongest IMFs are going to take the most energy to undergo a phase change. So IMFs, or intermolecular forces, are the attractive forces that exist between molecules. So intermolecular means between molecules, and so it's how whole molecules are attracted to each other. So here, between HCl, we have an intermolecular force, or an intermolecular attraction between the chlorine on one molecule and the hydrogen on an adjacent molecule. Versus intramolecular forces, those are the forces between atoms that bond atoms together. So an intramolecular force would be this bond. And intermolecular forces are between entire molecules to determine how molecules interact with each other in a solution, or in a solid, or in a gas. So the strength of these intermolecular forces, these cohesive attractive forces between molecules, is going to determine whether compounds have high or low melting points or high or low boiling points, and thus determine whether a substance is a solid, a liquid, or a gas at a given temperature, with a given amount of kinetic energy. And so these attractive intramolecular forces that hold bonds together are much stronger than the intermolecular forces between molecules. So just to kind of put things in perspective, when we're talking about bonds, like making ionic bonds and covalent bonds, the attractive forces that make an ionic bond, right, those oppositely charged cations and anions attracting each other, are kind of the strongest type of attraction we get to hold those atoms together in a chemical bond. And then sharing electrons is also very strong, a very strong type of attraction to make a covalent bond. And so both types of bonds, or intramolecular force, within a molecule are very, very strong. And then we see all these like greater than signs, right? They're very, very much stronger than IMFs. Intermolecular forces are significantly weaker than the forces that make bonds. So it's a lot easier to disrupt the forces that hold molecules together in like a solution than it is to disrupt the forces that hold atoms together within a molecule. So I just like to point out kind of that distinction that when we're talking about IMFs, we're talking about the attractions between molecules, and they matter, right? They affect the melting point and the boiling point, but they're not nearly as strong as the forces that hold chemical bonds together. It takes a lot more energy to break a chemical bond than it does to disrupt an intermolecular force and get a solution to, say, undergo a phase change from a liquid to a gas. So there's 3 types of intermolecular forces. And so they're shown here, kind of summarized in this table. London dispersion forces are the weakest, and all molecules can have London dispersion forces. So anything with covalent bonds, right, we're talking about molecules, can have London dispersion forces. They're inherent, just part of every molecule. The second type of IMF is the dipole-dipole interaction. These are kind of moderate or medium in strength. And any molecule that has a net dipole, that's polar, can have a dipole-dipole interaction. And then hydrogen bonding is the third type of IMF. It's the strongest. And in order for something to be able to hydrogen bond, it has to have an oxygen to hydrogen bond, a nitrogen to hydrogen bond, or a hydrogen to fluorine bond. And so hydrogen bonding is like a specialized type of dipole-dipole that's especially strong, and it's so strong that it gets its own name. So we have London dispersion, all molecules get that. Dipole-dipole, you have to have a dipole on your molecule, which means you have a polar compound. And then a special type of dipole-dipole bonding is called hydrogen bonding, which is the strongest type of IMF. And to hydrogen bond, a molecule has to have an oxygen to hydrogen bond, a nitrogen to hydrogen bond, or a fluorine to hydrogen bond. So the strength of different London dispersion forces, LDFs, is determined by the molecule size. So bigger molecules are going to have stronger LDFs. So if you're comparing 2 molecules that only have London dispersion forces and you're trying to figure out which one of those 2 has the strongest LDF, look for the bigger one. And we're going to talk about why here in a few slides. When you're comparing molecules that have dipole-dipole interactions, the strength of the dipole is determined by the magnitude of the molecule polarity. So more polar molecules are going to have stronger dipole-dipole interactions. And then for hydrogen bonding, the strength of the hydrogen bond is determined by the electronegativity of the atoms. So the greater the electronegativity, the stronger the hydrogen bond. So a hydrogen to fluorine hydrogen bond is going to be a stronger hydrogen bond than a nitrogen to hydrogen bond, because fluorine is more electronegative than nitrogen. Okay, so let's go through these in a little bit more detail one by one. Start out with London dispersion forces. These are our weakest type of intermolecular force. London dispersion forces are due to just a momentary, temporary change in electron density around a molecule. So what can happen is that even with a nonpolar molecule like CH4, shown here, CH4 has all nonpolar bonds. It's a tetrahedral shape. It's completely symmetrical. So it's a nonpolar molecule. But what can happen is that electrons are being shared in these bonds, and there's also electrons around the hydrogen, around the carbon. What can happen is that just for a moment in time, the electrons can shift to one side of the molecule. So if the electrons shift, say, to the left side of the molecule here, because there's more electron density temporarily, just due to this like momentary shift on one side of the molecule is going to be partially negative, delta negative. And because all the electrons shifted to one side, that means the other side of the molecule doesn't have as many electrons, so it's going to be delta positive. And when this happens, like it might just temporarily randomly happen in one molecule, it can induce the same thing to happen in the next molecule, because this one now has a partially positive side. It's going to attract electrons to it. So it's going to induce the one next to it to swing its electrons over to the side so the opposite charges can be attracted to each other. And when opposite charges are attracted, the partially negative side of the left molecule being attracted to the partially negative side of the right molecule, you get this temporary intermolecular force called a London dispersion force. And so because all types of matter, including covalent or molecular compounds, even nonpolar ones, are going to have these like momentary shifts in electrons, any type of matter can have a London dispersion force. So by default, every molecule is going to have LDF. So the magnitude, like the strength of the LDF, is going to depend on the size of the molecule or the size of the atom, because London dispersion forces are based on kind of this temporary shift in electron density to one side of the molecule. All right, we got our delta negative shifting over here, inducing the delta positive on this side. So the bigger the molecule, like the bigger the surface area, the bigger this like zone is going to be of the temporary shift, which means it's going to cause more attraction. And so what we see is that bigger atoms are going to have higher boiling points because there's going to have higher LDFs, like stronger London dispersion forces. And if there's a stronger London dispersion force, there's more attraction between the molecules or between the atoms, which means it's going to take more energy to get them to break apart and go from a liquid to a gas, which means the boiling point, the amount of energy, like the heat you have to add to get that transition to happen, is going to be more. So helium's a really tiny atom, right? It only has an atomic mass of about 4. So if we look at 2 helium atoms, they can undergo this temporary London dispersion force where we get one side that's delta positive and one side that's delta negative, and then it's going to induce a delta positive next to it and a delta negative, right? And you get the little bit of attraction here, our little temporary London dispersion force. Compare that to something like radon, which is a lot bigger atom. It's going to do the same thing where you get one side that's delta positive, one side that's momentarily delta negative, inducing a delta positive here. And then you get so much more attraction between these two because there's just more delta negative and more delta positive. And so bigger atoms and bigger molecules are going to have larger or stronger London dispersion forces. And the stronger the intermolecular force, the more energy it's going to take to disrupt the cohesive forces caused by that intermolecular force. And the more energy it takes to disrupt the cohesive forces, the more energy it takes to go from a state that's dominated more by cohesion, like solid to a liquid or a liquid to a gas, to go from one of those physical states that's held together by more cohesive forces. It's going to take more energy to disrupt and break apart those cohesive forces. So substances that have stronger IMFs are going to have higher boiling points and higher melting points. So if two substances only have London dispersion forces, they only have the weakest of the IMFs, you can still figure out which one's going to have a higher boiling point based on which one is bigger. The bigger one is going to have a higher boiling point because there's just more surface area for the London dispersion force to act upon. Okay, our next intermolecular force is called dipole-dipole interaction. Number 2. It's kind of our medium or moderate strength IMF. So dipole-dipole interactions are the attractive forces between the permanent dipoles of 2 polar molecules. And so when we say permanent dipole, what we mean is that the dipole is built into the structure of the molecule. With London dispersion forces, it was a temporary dipole caused by just like the random movement of electrons temporarily shifting from one side of the molecule to the other. In dipole-dipole interactions, each molecule has its own dipole that it always has due to its structure. And so when you check for dipole-dipole interactions, you're looking for molecules that are polar, because polar molecules are going to have this dipole arrow for the whole molecule due to one side of the molecule permanently being delta negative and one side of the molecule being permanently delta positive due to the structure of the molecule. So if we check out formaldehyde here, CH2O, the carbon to hydrogen bonds are nonpolar. So there's not much dipole in those bonds, but the carbon to oxygen bond is polar. So there's a dipole between carbon and oxygen. This molecule has an asymmetrical shape. It's an asymmetrical electron distribution where you have like more electrons on this side because oxygen's pulling them towards itself. More electron density, which means that this side of the molecule is partially negatively charged. Because the electrons are being pulled towards oxygen, that leaves the other side of the molecule not having as many electrons, so it's partially positive. So anytime you have this molecule that permanently has one side partially negative and one side partially positive, that's going to be a polar molecule. And we talked about how to figure out if something's polar or not towards the end of chapter 5. So a dipole-dipole interaction happens when you have polar molecules next to each other. So what'll happen is the partial negative side of one polar molecule is going to line up with the partial positive side of another polar molecule because opposite charges attract. And so they'll be attracted to each other and kind of stick together more with that cohesive force. So it's going to take more energy to break this up and get these particles to switch from being like a liquid where they're touching and attracted to each other to a gas where they're totally separated. So again, molecules with dipole moments that have that partial positive and partial negative side of the molecule are going to be electrostatically attracted to each other by lining up so that the positive and the negative ends are close to each other. So if we look at this example here, chlorine is less electronegative than fluorine, so it's delta positive. Fluorine is delta negative. So it's going to line up with the delta positive end of another F to Cl molecule to make this kind of attraction between the two. And there's another attraction. So with all these attractions between molecules, they kind of stick together more. And so it's going to take more energy to get them to separate. Like if you wanted them to go from a liquid where they're all touching and attracted to each other to a gas where they're acting completely independently of each other. So the greater the polarity of the molecule, the greater the strength of the dipole-dipole interaction. And you can figure out the polarity of the molecule by checking the delta En between the bonds and kind of looking at the overall molecular structure to see if those bond dipoles cancel out or if they reinforce each other to give you an overall polar molecule and like just how polar it is. So things to check for when you want to identify if a molecule can have a dipole-dipole interaction. You want to look for the asymmetrical shape and if it has polar bonds, because this is going to clue you into if the molecule overall is polar or not. So molecules that have an asymmetrical shape, they're going to be polar. And if they have polar bonds, if those polar bonds reinforce each other with their bond dipoles, then the molecule will also be polar. So for example, let's draw CH4. CH4 has all nonpolar bonds. Each carbon to hydrogen bond is nonpolar. So all of the bond dipoles, they're going to be super tiny, right? Nonpolar bonds, but carbon's a little bit more electronegative than hydrogen. So a little bit of electron pull towards the middle. But since the shape is symmetrical, it's a perfect tetrahedral, all these bond dipoles cancel each other out and you end up with a nonpolar molecule. But if we replace two of the hydrogens with chlorines, we still have nonpolar bonds between carbon and hydrogen, but now we have polar bonds between carbon and chlorine, where the chlorines are going to be pulling electrons towards themselves, resulting in this side of the molecule being delta negative, this side of the molecule being delta positive. So overall, you have a polar molecule. So polar molecules are going to have dipole-dipole interactions. So then you identify the direction of the dipole. If we bring that back, right, we've got the dipole moving across this molecule this way towards the delta negative side. If we draw a big arrow, right, this is the more negative side, this is the more positive side. And so the negative side of this molecule is going to line up with the positive side of an adjacent molecule so that the charges, the opposite charges, are being attracted to each other. And that attraction is what causes these solutions that have dipole-dipole interactions to be kind of more sticky, more cohesive. And so it's going to take more energy, like a higher melting point or a higher boiling point, to get them to undergo those phase transitions that take energy to undergo the transition. Okay, our third type of intermolecular force, hydrogen bonding. This is the strongest type of intermolecular force. So for hydrogen bonding to occur, the things to look for is you have to have a hydrogen atom bonded to an oxygen, a nitrogen, or a fluorine. So if we look at water, H2O, in water you have a hydrogen bonded to an oxygen, so this can participate in hydrogen bonding. So to see if something can hydrogen bond, you want to scan the structure to see if you have any oxygens bonded to hydrogens, nitrogens bonded to hydrogens, or fluorines bonded to hydrogens. And if you do, then the IMF that molecule has, the strongest one, is going to be hydrogen bonding. So in hydrogen bonding, what happens is that this bond between oxygen and hydrogen, or between hydrogen and fluorine, or hydrogen and nitrogen, it's got like a super dipole. So what happens is, right, you get a bond dipole where hydrogen ends up being really delta positive, and oxygen here, especially with its lone pairs of electrons, ends up being really delta negative. The electrons aren't completely transferred like in an ionic bond, but they're pulled really close to oxygen. So oxygen ends up being like really delta negative, and hydrogen ends up being really delta positive. And then the opposite charges on adjacent molecules are going to attract. So the super delta negative oxygen on one is going to be attracted to the super delta positive hydrogen on an adjacent molecule. So if we look at water in detail, water can form 4 hydrogen bonds. H2O can make 4 hydrogen bonds. If we look at the water molecule in the center here, we look at that one, it's got 2 hydrogens on it that are delta positive that are going to be attracted to the delta negative part of adjacent water molecules. So there's 2 of our hydrogen bonds. And then oxygen has 2 lone pairs of electrons. That's the delta negative part, which can be attracted to the delta positive part on adjacent water molecules. So water can make 4 hydrogen bonds. It's like a popular quiz or test question. Draw the structure of water and predict how many hydrogen bonds it can make. It can make 2 from its 2 hydrogens being attracted to 2 other delta negatives. And it can also attract 2 hydrogens due to its 2 lone pairs of electrons, the delta negative part of the water molecule itself. Checking out some more hydrogen bonds. Again, remember, to have hydrogen bonding, you have to have an H atom bonded to a fluorine, nitrogen, or oxygen. If we look at acetic acid here, in acetic acid, you're going to get, you have oxygen connected to hydrogen, so you can have hydrogen bonding. And so this delta positive hydrogen is going to be attracted to a delta negative oxygen on an adjacent molecule, and that's your hydrogen bond. So you have to check that you're able to do it, and then if you're able to do it, then this is the actual hydrogen bond. And same thing here, down below. This oxygen is delta negative, this hydrogen is delta positive. This allows us to make that special hydrogen bond, and then this is the actual hydrogen bond. If we check out ammonia, NH3. NH3 has nitrogen attached to hydrogen, so it can make hydrogen bonds. And so the delta positive hydrogen on one ammonia is going to be attracted to the delta negative part of an adjacent ammonia, which is the lone pair of electrons on that nitrogen. And then the delta positive on this ammonia is going to be attracted to the delta negative on the adjacent ammonia. Just a note, we draw hydrogen bonds with a dotted line because they're not really a bond. The electrons aren't being shared or transferred between the atoms involved in a hydrogen bond, there's just a really strong attraction. So I kind of put bond in parentheses here. We call it hydrogen bonding, but we don't draw it as a straight line because it's not an actual chemical bond where electrons have been transferred or where electrons are being shared. It's just a very strong attraction between hydrogen and another electronegative atom. So hydrogen bonding has a big influence on the boiling point of water, which I think is really great for the existence of human life, because based on periodic table trends, if we look at other elements in the same group of the periodic table as oxygen, so group 16, so we look at like oxygen with two hydrogens, water. We look at sulfur, H2S, we look at selenium, H2Se, and we look at beryllium, H2Te. If we track their boiling points, there's like a pretty linear relationship going from beryllium to selenium to sulfur, with the boiling point decreasing as you move up the periodic table. The boiling point is decreasing as you move up the periodic table because the atoms are getting smaller as you move up the periodic table. So the London dispersion forces are going down, which you would expect there to be then lower boiling points with weaker London dispersion forces. So the predicted boiling point of water would be -80. Can you imagine if water boiled at -80 degrees Celsius? That means that most of the water on Earth, because most of the Earth is not at -80 degrees Celsius, most of the water at Earth would always be in the vapor phase. We'd have very little liquid water because most of the Earth is above -80 degrees Celsius. But the actual boiling point of water is 100 degrees Celsius. It deviates significantly from this trend predicted from the periodic table. And that's because water can hydrogen bond. And those hydrogen bonds are the strongest cohesive forces that can exist between molecules. And so because of hydrogen bonding, water molecules kind of stick to each other, and it takes a lot more energy to get them to convert from the liquid phase into the gas phase. So that's why their boiling point is so high. Hydrogen bonding is also really important in biology. As you take bio classes, you'll talk more about hydrogen bonding. The double helix structure that makes up DNA is formed due to hydrogen bonding between nucleotides. So DNA consists of these chemical structures here called nucleotides that stick off the backbone of the DNA. And so if we zoom in, here's our backbone, and then here's our nucleotide, the chemical structure of the nucleotide. And nucleotides contain hydrogen bonds. See, we have a nitrogen to hydrogen right there. And so the nucleotide on one side of the DNA strand is attracted through a hydrogen bond to the nitrogen on a nucleotide on the other strand. So we're looking like here to here with hydrogen bonds. And it's those hydrogen bonds across the DNA strands and their attraction that pull the strands together and end up twisting it into this double helix structure. This is also seen in the folding of proteins and enzymes. Proteins and enzymes have to fold into just the right three-dimensional structure for them to be active or inactive, for them to basically undergo their proper biological function. Their folding is based on typically hydrogen bonding happening across parts of the protein to bring it in close together and fold it over on itself in just the right arrangement. So let's do a quick concept check. So with respect to intermolecular forces in a liquid, which one is the strongest? Dipole-dipole interactions, hydrogen bonding, London forces, or no correct response? Hopefully you can answer this one as hydrogen bonding is the strongest IMF. Dipole-dipole is our moderate. And London dispersion forces are the weakest. Okay, so to summarize IMFs, intermolecular forces are the attractive forces that exist between molecules. There's 3 of them. London dispersion forces, these are the weakest. and all molecules have London dispersion forces, and we can differentiate London dispersion forces, like which LDF is stronger than another, by the molecule size. So bigger molecules are going to have stronger LDFs. Our next IMF is dipole-dipole. It's kind of in the middle. It's a moderate strength. And molecules that have a net dipole, or molecules that are polar, are going to have a dipole-dipole interactions. And it's when the delta negative end of one molecule lines up with the delta positive end of another molecule to kind of hold them together. And so the more polar the molecule, the stronger the dipole-dipole interaction. Our third IMF and strongest is hydrogen bonding. And so for something to hydrogen bond, it needs to have an oxygen to hydrogen bond, or a nitrogen to hydrogen bond, or a fluorine to hydrogen bond. And the example we went over was water. It can make 4 hydrogen bonds. And it's these hydrogen bonds that give water its unique properties. We would expect water to have a boiling point at negative 80 degrees Celsius if it followed the trends of the other atoms in its on the periodic table. But because water can hydrogen bond, it has a significantly higher boiling point. So the boiling point of water, instead of being negative 80, like predicted based on periodic trends, is actually 100 degrees Celsius. And that's because it takes so much more energy to break up these incredibly strong attractive forces to get water to go from a liquid phase to a vapor phase. So for hydrogen bonding, the greater the electronegativity, the stronger the hydrogen bond. So fluorine to hydrogen, the fluorine is going to make a stronger hydrogen bond than, say, oxygen to hydrogen, because fluorine is more electronegative than oxygen. So the stronger the IMF, the more energy it will take to overcome the cohesive forces that are attracting particles of a substance together. Stronger IMF means more cohesive forces, like stronger cohesive forces. So substances with stronger IMFs typically have higher melting and boiling points. It's going to take more energy, like more heat, to get them to undergo a phase transition from solid to liquid or from liquid to gas. So to kind of summarize the effect of IMF on the phases, when the IMFs are weak, you have compounds that tend to have high volatility, meaning they easily convert from a liquid into a gas if they have weak IMFs. If they easily convert from a liquid into a gas, that means there's going to be a lot of that substance in the gas phase, so the vapor pressure is going to be high, and the boiling point is going to be low. Like, it doesn't take much heat, doesn't take much energy to get it to boil. When the IMFs are strong, the volatility is going to be low. Not much of the substance is going to be able to convert from a liquid into a gas without adding additional heat. So low volatility with strong IMFs, because the molecules are being held together with those strong cohesive forces in the liquid phase. That means the vapor pressure is going to be low, because there won't be many molecules in the vapor phase, which means the boiling point is going to be high. It's going to take a lot more energy, like a higher temperature, to get that substance to boil, to break up those cohesive forces. So I'm going to, after this lecture, do an extra one where I just go through a few example problems on intermolecular forces in liquids. So if you want to see how we look at structures of molecules, determine the IMF, and then rank the boiling points or the melting points, those are the types of example problems I'm going to do in the next lecture. Hope to see you then. Thanks.